I'm going to go over the Math 3 Unit 6 Worksheet 2, doing a few of these problems, and we're going to start with number 3. 3, we have an index of 4. We're looking at the 4th root of 64, x to the 6th, y to the 7th. So we want to break down 64, and we're looking for sets of 4 numbers. So 64 is 8 times 8, and the 8s can be broken down to 4 times 2, and the 4s can be broken down to 2 times 2. And so we end up with 6 2's, and so we got one set of 4 2's and then 2 that are left over. We have 6 x's, so one group of 4, 2 left over, and 7 y's. So one group of 4 and 3 left over. So everything I circled we can take the 4th root of, and so we end up with 2x y, and then 4th root of everything I didn't circle. Well, so we got the 2 times 2, I'll highlight them, so 2 times 2, and then we got a x squared, and then we got the y cubed, so 4x squared y cubed. Because the index is even, when we take the 4th root of a number, we need to make sure we get a positive answer. And so the x we need to put an absolute value around, and the y we need to put an absolute value around. Number 9 is the next one. We were asked to multiply and simplify if possible, and we're going to assume that all variable expressions are real numbers. So on number 9 we have a product of 2 cube roots, and as long as we're working with real numbers, we have the nth root of a times the nth root of b in general will be the nth root of a times b. That's a rule we can use as long as we're working with real numbers. Here we have real numbers, and so this is equivalent to the cube root of, well, negative times negative is positive, so 12 times 18. And there's no reason to multiply them together because we're going to end up breaking them up anyways. And so now we're going to break these numbers down. 12 is 4 times 3. 18, 3 times 6. 4 is 2 times 2. 6 is 2 times 3. And so notice we have 3 2's and we have 3 3's. And so this is going to equal 2 times 3, which is 6. Number 13. So here we're assuming we're working with real expressions here because we have variables, and the x and the 2x are on the outside of the cube root, and so we can multiply those together and get 2x squared. And then we have the cube root of 27. We've got an x squared times x cubed, so that's x to the 5th, and a y. So we're multiplying the things on the outside with things on the outside, and everything on the inside of that cube root with everything on the inside of the cube root. That's my first step. Now then I'm going to try to simplify that cube root. 27 is 9 times 3, and 9 is 3 times 3. So we get a set of 3 3s. We got 5 x's and 1 y. And so we already had the 2x squared on the outside. And then we're able to take the cube root of 3 times 3 times 3, which is 3. And we're able to take the cube root of x times x times x, which is x. And then we have some leftovers. So left over with the cube root of x squared and a y. And then we can multiply the 2 and 3 together and you get 6. X squared times x, get x cubed. And then we have the cube root of x squared y. And no need to think about absolute value because the index that we were working with here is odd, and we're working with cube roots. 15. We have a 3 out in front, so and a 1 here, so 3 times 1 is 3. Times the square root, we got a 2, a to the 5th and a to the 7th. When you multiply, you add those exponents, so you get a to the 12th. And b to the 5th times b to the 6th, add those exponents, you get b to the 11th. And then try to simplify. We only have 1, 2, so that's going to stay beneath. We have 12 a's, so that's going to give us 6 sets of 2. And 11 b's. So we get 5 sets of 2 and 1 remaining. So we're able to take the square root of a to the 12th and b to the 10th, and we end up with 3 a to the 6th, b to the 5th, square root of 2b. And because our index is 2, we're working with the square root, we need to think about, we look at our variables that we pulled out. So we got a to the 6th. If you have an even power, it's going to make that positive, even if a were negative. So that does not need an absolute value, but the b to the 5th does. Now, some may argue that we don't need to put that absolute value around the b to the 5th because we were assuming that a to the 5th, b to the 5th was real, and so therefore b could not be negative, because if b was negative, then a would have to be negative to make the first part real, but then the second part wouldn't be real because a would be negative and contribute that negative. And so you could make an elaborate argument that b would have to be positive and we wouldn't need the absolute value, and you'd have a basis for that. And so we could also accept 3a to the 6th, b to the 5th, square root of 2b. Number 17, we have 2 cube roots. What's in front? We got a negative 1 times a 4, so that gives us negative 4. And then the cube root of 2 times 12, 24. X to the 3rd times x to the 5th, x to the 8th. You add those exponents. Y squared times y, which is y to the 3rd. Break down the 24. I'm going to make it 6 times 4. And 6 is 3 times 2, 4 is 2 times 2, and we're looking for sets of 3 numbers. So we got 3 2's here with the remaining 3. 8 x's. And 3 y's. So the 3 and the 2 x's remain underneath the cube root, but everything else we're able to take the cube root of. So we already had a negative 4 and out in front, and then we're able to take the cube root of 2 times 2 times 2, which is 2, and then x times x, and then y, and we're left with the cube root of 3 times x times x. So this gives us negative 8x squared y times the cube root of 3x squared. Number 19, we're asked to distribute here. We're multiplying square root of 6 times square root of 6 and square root of 6 times the square root of 18. So that's going to give us the square root of 6 times 6, which we got a pair there, plus the square root of 18 times 6. And 18 times 6, well, 18 is 3 times 6. So there's a pair of 6's and a 3 left out. And so we end up with 6 plus 6 square root of 3. And you might be tempted to add the 6 and 6 and get 12 square root of 3, but we can't do that. We need to follow order of operations, which states we need to multiply the 6 and the root 3 first before we add that 6. And so this is as far as we can go. Number 21, we're asked to simplify each expression, rationalize all denominators, and assume all variables represent positive numbers. If you have a root, same root, so here the index is the same, we got a square root of 5 or a square root of 10, you can reduce as if this were a fraction. So you can divide top and bottom by square root of 5, and you end up with square root of 1 over the square root of 2. We know the square root of 1 is 1, so this is really 1 over the square root of 2. The denominator is not rational, it's irrational right now, and so we need to rationalize it by multiplying by square root of 2 over square root of 2. So when we do that, we end up with the square root of 2 times 1 over the square root of 2 times the square root of 2, which we got a pair of 2's, and so that's going to be the square root of 2 over 2. And now we have a fraction where the denominator is a rational number, an integer, and that's our answer. 23, we have 2 over the cube root of 6, and 6 is 2 times 3. To get rid of our cube root, we're going to have to be able to create a set of 3 things. We only have 1 2 and 1 3, so we need 2 more of them. So I'm going to need to multiply by 2 more 6's. And whatever I multiply the bottom by, I'm going to multiply the top by, so that this second fraction is equivalent to 1. So we're multiplying our first fraction by 1, which does not change its value. So we get 2 cube root of 6 times 6, which is 36, divided by the cube root of 3 6's. We have a set of 3 there, so that is 2 cube root of 36 over 6. And then we can reduce our numbers, the 2 and the 6, divide them by 2, and you end up with 1 cube root of 36 over 3. We cannot divide the 36 by 3. 1's underneath the cube root, 1 is not. Number 27. What we have here is 8 over the cube root of 5 times 5 times x times x. So we already have two 5's and we already have two x's. We need to get rid of the cube root because we want to make our denominator rational. And so we need to create a set of three things. So we want a cube root of, well, we already have two 5's, so we only need one more 5. We already have two x's, so we only need one more x. So cube root of 5x. Which has a value of 1. Right? Because cube root of 5x over cube root of 5x is 1. So we're multiplying our fraction by 1, maintaining its original value. And we end up with 8 cube root of 5x over the cube root of, now we got 3 5's and 3 x's. So we can take the cube root of each of those, and we get 8 cube root of 5x over 5x. And there's nothing to reduce now. That's as much as we can do to that fraction. Here we can reduce a little bit. The y's we can cancel out, and I'm going to divide top and bottom by 2 x's. I could divide by 3 x's, but that leaves me with 1 x, but now I want to create pairs of x's, so I'm going to divide by 2 x's, and so after I simplify this, I get 2 square root of 7x over negative 3 square root of 12x squared, which is x times x. So I already have my pair of x's. 12 is 2 times 2 times 3. So I already have a pair of 2's. So I'm going to simplify this denominator. And I get 2 square root of 7x over negative 3 times 2 times x square root of 3. Twos can cancel out, or you can divide top and bottom by 2. And the only thing I need to get rid of is that square root of 3, so I'm going to multiply top and bottom by root 3. And we end up with 7 times 3 is 21, so square root of 21x over x times the square root of 3 times 3. There's our pairs of 3 there, and we can get rid of that. So square root of 21x all over 3x. Number 31, last one here. We need to determine whether the expression is equivalent, which each expression is equivalent to the cube root of 81 x to the 7th. So the cube root of 81 x to the 7th. 81 is 9 times 9. 9 is 3 times 3. Looking for sets of 3 things. X to the 7th. Okay, so let's see what happens here. So our first expression is 3 cube root of 3x to the 7th. So they kept the x to the 7th, but they no longer have that 81. They have a 3 underneath, so they changed the 81 only. So if we change the 81 only for ourselves, we would get 3 cube root, there's a 3 left over, x to the 7th, which is exactly what they have, so that's a yes. The next one, again, they got rid of the 81, or they worked on the 81, and they were able to get rid of everything, but that's impossible for us, so we know that's not true, that's false. The next one, they brought the 3 up, but they also dealt with the x to the 7th. And if we did that, we circled 2 sets of 3 x's, so we should have 3x squared cube root of 3, and there's a remaining x, which is exactly what they put, so that's a yes on the third row there. And then the last one, they left 4 x's and they got rid of the others. So if we left the 4 x's, then we just moved the others, we would have 3x cube root of 3x to the 4th. That is correct, so yes. So the first, third, and fourth rows are correct.